Right. Yeah. Yeah. Like I was just looking at the practice exam or the practice problem, specifically this problem here. I believe you would have to do this as the first order linear differential equation. So ignore that.
So
That's
if we ignore this.
right. Yeah. That one is not doable as a separable differential equation. Right. If you read this question, right, solve the following differential equations. This one cannot be separated. So the only so no, it's not. It's actually something that's not in the textbook. So if you actually look ahead to the homework assignments, if you look at like we're right here, right? At, we're on 217 holiday 219 test. That's 214 was section 7.4, and then for the next part, the next section is from the handout. So right, the next first order linear differential equation stuff, which will not be on the second exam, is not in your textbook. I assume so. We'll certainly talk about it in class on Thursday. Right. I think we did one or two examples last Thursday, I think. So yeah. So um yeah, I don't think I looked for it on campus. I didn't see it there. So I don't think it's been posted yet, or handed out.
Maybe co-class too.
You mean like the discussion? Yeah, yeah. I'm not handing it out for him. Couple other things. So if you haven't yet, do make sure that you take the practice exam that I posted and then either look at the solutions and or watch the video of me going over the solutions. There was a very small error on the practice exam I posted where I like forgot the lower bound of one of the intervals for an integral, but it's not like I think I fixed it, but I also covered it in the solution, so it shouldn't be too big a deal. I think that's all I want to say as far as like logistics stuff. I feel like I'm forgetting something, but oh well. All right, questions. Volume, okay. Okay, so I don't have the textbook for no, I don't have the textbook on me. Do I? Yeah. Yeah, technically I have a PDF of the flight. That's the volume. Warm out there? Warm in here. Oh, and also I forgot to print out that's what it was. I forgot to print out an name sheet, but you could write your name on the name sheet. Legibly. And you can do some volume. I will point out while you look, definition. When it comes to volume questions, most of the volume questions you get asked are usually about setting up. Not that you wouldn't ever have to evaluate one, but the setting up is the harder part typically when we think about these. She said 15 to start with. Oh yeah. So okay. So I would also point out that these ones specifically are the more terrible ones. Usually the volumes of so I should say these ones, the volumes of revolution are usually the ones that are more to set up. These ones with the base being a thing are kind of terrible. So let's look at this first one, 15. The base of S, the solid, is an elliptical region with a boundary curve of 9x squared plus 4y squared equals 36 is the boundary of our base. So what we should be thinking is on the floor, you've got an ellipse. And then popping up out of that ellipse is cross-section perpendicular to the x-axis are isosceles, right triangles with hypotenuse in the base. Okay, so you don't have to draw this picture, but you have to be able to imagine it. So here's what I'm imagining. I've got some ellipse, and let me ask you all a question. Based on this equation, 9x squared plus 4y squared equal to 36 is the horizontal axis or the vertical axis the longer one? Good question. So think about what your intercepts would be. If you plug in 0 for x and you have 4y squared equal to 36, your y-intercepts are going to be plus or minus 3. If you set y equal to 0 and you set 9x squared equal to 36, your x-intercepts are going to be plus or minus 2. Right? Because 36 divided by 9 is 4. The square root of 4 is 2. Just like square root of 9 was 3. So our ellipse has a longer y-axis or a longer vertical axis. So we're thinking about drawing this ellipse in 2 dimensions. It has y, and really the way you do it is you just find the intercepts. Like that is the way you find how the ellipse looks. Look vaguely like this. And the idea is out of that. And now here it's important to read the question carefully. I'm sorry. Your cross sections are perpendicular to the x-axis. Our cross sections look like this. And they are popping up out like isosceles right triangles. So when you read these ones where they give you the shape of the base and they say cross sections perpendicular to whatever, you're supposed to imagine like the base of that cross section perpendicular to the axis that they mentioned, in this case the x-axis, and then the rest of the shape is popping out in the 3rd dimension, right, towards you. Okay, so there's kind of 2 pieces to this process every time. You have to find the volume of your slice. So and you're supposed to give your little cross section a little bit of thickness here. So the volume of our slice is going to be the thickness of the slice, dx, times the area of the triangle. So it's the area of our triangle times the thickness, which is dx. And I usually like to start off by, depending on what shape I've got here, either calling the length of this L if I need the entire length, or like if I just need, like if I'm thinking like a semicircle, I usually just call the 1/2 the length R for the radius of the semicircle. So I'm thinking though that this entire length here, whatever that is, which we'll figure out in a minute here, that's L. I know that the area of a triangle is 1/2 times the base times the height. So that's going to be 1/2 times the base times the height. And I'm making up letters right now, right? I'm just using letters that are convenient. I'm like, cool, here's my triangle down here. I'm going to draw it again to make it easier to figure out what's going on. I didn't draw it very well. My triangle has a length of L, I'm sorry, a base of L, and a height of H. But they told us something about the triangles, right? So typically they're going to tell you the triangles are equilateral, which is like the worst case scenario. Or the better case scenario here is that the triangles are isosceles right triangles with hypotenuse in the base. So that means, and I've drawn this really poorly. This is supposed to be an isosceles triangle that's a right triangle whose hypotenuse is lying in the base. So great. If that's L, let's find these other 2 sides here. Right? So I'm going to say that x squared plus x squared equals L squared. And really, if I was smart about this, instead of trying to just solve for L or for X here, I would say, well, another way of writing the area of this triangle is it's 1/2 X times X, right? You can reorient the triangle to look like this. X, X, L. That is another valid way of drawing the triangle. So X is a poor choice here. I should not be using X because X is already spoken for, right? If when I go back here, so let me pick a different letter. Sorry about that. Let's call it A because I can kind of turn my X into an A pretty easily here. So the area of my triangle is 1/2 A times A. But now I'm going to work back to get in terms of L. Well, L squared is equal to 2A squared. So A squared is equal to 1/2 L squared. So that's going to be 1/2 times 1/2 L squared, which is 1/4 L squared. I'm sorry, I lost my dx along the way. Bless you. Okay, we're almost there. We just have to find this length in terms of the variable we actually need to work with. So it's going to be the top function minus the bottom function. So we're going to take this ellipse equation and so the top is this part, the bottom is this part. It's kind of like when you find the equation, when you have the equation of a circle and you find the top half and the bottom half by doing the positive part of the root and the negative part of the root. That's what we're going to do right here. So solving for y, we have that 4y squared equals 36 minus 9x squared. Divide both sides by 4. Yeah, divide both sides by 4. You get y squared equal to 9 minus 9/4 x squared. And then you get y equal to plus or minus the square root of 9 minus 9/4 x squared. So the top piece is the positive root. The bottom piece is the negative root. So your L there is equal to the top piece minus the bottom piece, which is just going to double your root. It's going to be the positive square root of whatever minus the negative square root of the same thing. It ends up being 2 times the square root of 9 minus 9/4 x squared. Which means that we can rewrite this as, space, sorry, done a poor job of spacing this out, that the volume of our slice we can finally end up writing as 1/4 times our length, which is 2 times the square root of 9 minus 9/4 x squared dx. And then finally, we can write the integral because we're just going to add up all the slices from as far left as -2 to as far right as +2. What the thickness is the dx.
Oh,
So then our total volume is going to be the integral from -2 to 2 of 1/4 times 2 times the square root of 9 minus 9/4 x squared. Yes. Most of the time, these integrals actually end up being really, really easy. Look what's going to happen here. When I square this out, I get 1/4 times 2 squared is 4, and the square root of 9 minus 9/4 x squared is 9 minus 9/4 x squared. The 1/4 and the 4 cancel, you end up getting the integral from -2 to 2 of just 9 minus 9/4 x squared. I will freely admit that I might not have gotten through this problem in the most direct way possible. I'm just trying to show you the way that I'm thinking about it. I'm trying to make it show you in what I think is the easiest way to think about it possible, and that might not have occurred this time. Sometimes it's hard. Sometimes it can be challenging to wrap your head around, like, do I want to kind of figure out what the length is first, or do I want to figure out what the area equation of my thing is first? So there probably was a faster way to get there here. We could finish this problem, but if I want to find the rest of this is not the hard part, right? Doing this integral and plugging in 2 and -2 should be really, really straightforward. So I think we can leave it there. Let's do another one because they're kind of a pain. Let me just a quick question to myself here. I lost the page I'm looking for. I'm curious if there's any of these on his practice problems. Doesn't appear that there are. Oh no, there are. Yeah, there definitely is one. Nope, I take it back. So we'll do one more. I will point out I don't see any problems like this on the practice. Not that there couldn't be on the exam, just that. Yeah, I guess that's all I can really say is I can see. So do you want to look at which one did you say? 16. Okay, sure. Let's look at. Sure. Oh, that's terrible. All right, I might change one of these. That's fine. So let's actually. Yeah. So the base S. Okay, another one here. Yeah, fine. So another one where we have a base S is, let's say, yeah, you could do something like that, sure. Is a circular disc with a radius of R. Okay, so we're going to draw it. It's just a circle. Technically, it's the circle and all the inside parts of the circle, but okay, fine. And the radius is R. Okay. And the problem says parallel cross sections. You don't really need the word parallel there, but okay. Cross sections perpendicular to the base are isosceles triangles with a height of h. Now, they didn't say which axis. They didn't say perpendicular to the x or the y because in this case, it doesn't matter. right? Since it's a circular shape, either way you do it, it's going to end up with the same thing. Let's try going the other way just to kind of, just in case, right? Maybe it's going to be perpendicular to the y-axis instead of the x-axis. So let's draw perpendicular to the y-axis this time. So cross section is perpendicular to the y-axis. Are stupid. They are isosceles triangles with height h and unequal side in the base. They don't even want us to solve this one. Okay, this one's extra dumb. So it's it's isosceles triangle with a height of h. So I've got my triangle shooting up out like this. I know that this side and this side are the same. And I guess, and obviously the hypotenuse is not. Isosceles and unequal side in the base. Oh, I'm dumb. Okay, that's hard to read. So if it's isosceles and unequal side in the base, but it's not right. It's not a right triangle necessarily. So yeah, okay. Right, so your isosceles triangle could look like this, or it could look like this. Right, unlike before, right, we just know it's isosceles. So this side and this side are the same, and the unequal side is in the base. This seems extra silly. Okay, so we know that for our isosceles triangle, the height they told us is h. And the base is just however long it is from one side of your boundary to the other side of your boundary. So in this case, the base is going to be, right, exactly, the right function minus the left function. So our base, let's call it b, our base is equal to the right function minus the left function. So what's our equation? It's x squared plus y squared equals r squared. And so if we solve for x, because we have to do things in terms of y, oh yeah, I should say the volume over, no, we'll just do this. So we're gonna have x squared equal to r squared minus y squared, and x is gonna be the square root of r squared minus y squared. So then, oh sorry, plus or minus. So then the base is gonna be the positive square root minus the negative square root, which is just gonna end up being 2 times the square root. So our base is going to equal 2 times the square root of r squared minus y squared. Right function, which is x equal to the square root of r squared minus y squared, minus the left function, which is x equal to the negative square root of r squared minus y squared. So then we're going to find the volume of our slice. The volume of a slice is just going to be 1/2 times the base times the height times the thickness, which is dy. And in this case, right, we don't have a way of writing h in terms of our base. They didn't give that to us. They're only asking us to set this up. So in this case, we would just write this as 1/2 times 2 times the square root of r squared minus y squared times h dy. I think this is kind of a silly question, but okay. And then the total volume, we would integrate. I'm going to simplify this by canceling the 2's. It's going to be the square root of r squared minus y squared. I probably put the h in front just so that people reading it would know the h wasn't in the square root there. Back. And h dy from as far from as far down as negative r to as far up as positive r. But without a way of finding the height in terms of anything else, we can't do any more with this.
Very wordy.
Very wordy. Yes, these ones typically are. They're not great test questions, which hopefully means it won't come up on your exam, but that doesn't mean it couldn't. Yeah. A better shape, more typical shapes are like a semicircle coming out. So if this was a semicircle instead, if it was a semicircle, then what we would do, well, then our slice would be, I should use a different letter. I'll use a capital R. 1/2 our radius squared. So our volume would be the integral from negative R to R, 1/2 whatever your radius squared dy would be. And then your radius is just, well, it's the square root of R squared minus Y squared. And I forgot something important. What did I forget that's important for the area of a semicircle? I did divide by 2. What's the area of a, yeah, I forgot the pi. Right, it's 1/2 pi R squared. So there should be a pi in there. And then the radius is just that length, which is just the x value, which is the square root of R squared minus Y squared. So this would be equal to pi times the integral from negative R to R of 1/2 times your radius, which is the square root of R squared minus Y squared. That's a better shape typically. Okay, other things.
Decided for a converter.
Correct.
But before you actually do the process, I was really. There were some questions I were asking.
Yeah, interesting. So typically you have to evaluate the integral to decide. Although, so you should have some intuition. So looking at a couple of these examples, I'm going to change this one up a little bit. For example, the integral from, say, sure, 1 to, oh yeah, thanks. 1 to infinity of 1/1 plus x squared. We should have an idea if this is going to converge or diverge. Here's the way I would typically think of it. How do I think of it? So if you've got something like a 1 over, if you've got infinity as an improper limit of integration, if your integral is like 1 over x to a power that's larger than 1. I know that sounds not, but like, so basically integral of 1 over x going to diverge. Integral of 1 over x to the 1.00001 will converge if infinities, because essentially what's happening there is if you integrate that, if your power in the denominator is 1 smaller, you end up with something kind of in the numerator, for lack of a better word. And then the numerator going to infinity gets infinitely large. But if your power is just a little bit larger than 1 when you integrate it in the denominator, then you end up with something that's still in the denominator. So this to me says something, well, like I've got a 1 over x squared essentially. I'm pretty sure I'm going to integrate this and get something that's still going to get small as x gets larger and larger and larger. This is kind of a special case, right? This one's going to be, well, before I do anything, what should I write? The limit. You got to start with a limit as b goes to infinity of the integral from 1 to b of 1/1 plus x squared. You don't always have to do that in your life. You definitely have to do that on a test, right? They want to see that step. And then we integrate. And this one, it's going to be the arctangent. So it's the limit, b goes to infinity of 1. I wrote the integral again. Sorry. Apologies. I don't want the integral again. Of the arctangent of x from 1 to b. And we plug in. The limit is b goes to infinity of the arctangent of b minus the arctangent of 1. And you do have to know that as b goes to infinity, the arctangent function gets closer and closer to what? Pi over 2. What's the arctangent of 1? Pi over 4. And pi over 2 minus pi over 4 is pi over 4. So this integral converges to pi over 4. But to answer your question, I don't, even if, like, you should just do the integral. Like, and do it enough until you're sure it's either going to converge or diverge. And if it converges, you should finish it and be like, oh, it converges to whatever value you get, because usually that's what's being asked. On the other hand, we had something like this, the integral from, sure, like that, 1 to 3 of 1 over 3 minus x squared. I don't know. So here's what I want to point out. The thing I said about infinity is kind of the opposite of what's true for other types of problem points. So if you've got, yeah, let me just write down sports here. So we'll come back to this in a second. So basically, this is very, very general. I'm just writing this down for the sake of writing. If you have the integral of 1 over x to the p like this, it's usually going to diverge if p is less than or equal to 1. It's going to converge otherwise. None of that's like, I mean, this is true for this here, but it's kind of a general rule of thumb. Like if you have infinity and your power in the denominator is bigger than 1, you typically get convergence. Power is less than or equal to 1, typically get divergence. On the other hand, if you go the other way, if you have something like the integral from 0 to 1 of 1 over x to a power, now 0 is the problem. And usually you get the opposite kind of issue. This is going to diverge if your power is bigger than or equal to 1 and converge if your power is less than 1. Because the problem here is if your power is larger than 1, you still end up with like an x in the denominator. Great, infinity in the denominator means you're getting smaller and smaller and smaller. 0 in the denominator means you're getting division by 0. So that's why the thing that's an issue changes depending on what kind of thing you're looking at. And lucky you all, most other classes don't cover this second type of improper integral, but you do. Right? He did cover those, talking about the ones where you have, yeah, we definitely talked about those. Yeah. Where it's improper, not because of an infinity or a negative infinity, but because the function's undefined at 1 degree of integration. So we can write this as the limit as b approaches 3 from which side? Yep, from the left side. We know it's on the left because we're between 1 and 3. So we're definitely less than 3 or left of 3. Integral from 1 to b. I'm going to rewrite this as 3 minus x to the negative 2. We're going to integrate. The limit is b approaches 3 from the left. The antiderivative of 3 minus x to the negative 2 is 3 minus x to the negative 1 divided by negative 1, but also divided by another negative 1. Right, exactly. Chain rule. You could have done a u sub and let u equal 3 minus x, but I don't think you need to show all that work. So, and that's from 1 to b. Rewriting this in a more useful way, its limit is b approaches 3 from the left of 1 over 3 minus x from 1 to b. At this point, you should be able to see that this is going to diverge. So when we plug in b and then plug in 3 for b, you're going to get division by 0. I would probably write one more step and say, okay, it's the limit as b approaches 3 from the left of 1 over 3 minus b minus 1 over 3 minus 1. And if you plug in b approaching 3 from the left, you're going to get 1 over 3 minus 3, which is division by 0. So this diverges. If you wanted to be more informative, you could say it diverges to, well, since it's 1 divided by a slightly positive number, it's diverging to positive infinity.
Do you think on the test you can just write down very?
Probably, yes. I'm just trying to say everything I can say.
It's just not clear.
Right. Also, if you weren't sure, don't say anything. Just say it diverges, right? Like if you know it diverges, but you were asked to say it diverges to infinity or negative infinity, if you could see which one and you didn't know, just don't say it.
Like plus infinity minus infinity.
Divergence. Yeah. And then kind of doesn't really typically happen. Yeah. So it's divergent because we have a limit that doesn't exist. Right? So the integral is equal to the limit. If the limit does not exist, we say that the integral is divergent.
Well, b is tending to a value less than 3. So like,
Sure, but we're not asking about what b is getting close to. We're asking what the integral is getting close to. And the integral itself is what this entire limit's getting close to. This part here is getting infinitely large. Infinity minus half is still infinity. So is this integral getting close to any one particular number? Absolutely not. Right? Infinity is not a real number we're getting close to. Can you get close to infinity? No. You can keep going towards it, but you never get close to it. So it's kind of annoying that we say that the limit is infinity because that still means the limit doesn't exist. We're just trying to say more about the way in which it does not exist. So yeah, this integral diverges. The limit does not exist. This integral converges. The limit does exist. Yeah, Jonathan.
to.
From 3 minus x to the negative second to this.
Oh, I mean.
Mhm.
Or divided by.
Why did I divide by another negative one? So the reason I divided by another negative one here is because we did a u sub without actually showing the work. So the work that actually occurred when we did this integral was when we're doing the integral of 3 minus x to the negative second, what we did was we let u equal 3 minus x. We've done this before where if it's just a linear function of your thing, we often kind of skip the step. Your du would have been negative dx, negative du equals positive dx. Rewriting this, it's the integral of u to the negative second times negative du. Integrating that, you get negative u to the negative 1 divided by negative 1. So there's the thing we had. There's the extra negative that I'm talking about right there. And then that ends up becoming positive u to the negative 1, which is really 3 minus x to the negative 1, or 1 over 3 minus x. That's how we got there. Is that the question you had?
Yeah, that answers it.
So just as a quick kind of check here, if I asked you all to integrate cosine of 3x, you would get, what would you get? Sine of, right, divided by 3. That one's not too terrible, but it's a little trickier when you see this. The integral of like 1 over 2 minus 7x dx. That one I really think you can also do without doing the u sub. Because I know that you all know that the integral of 1 over x is what? Yeah, natural log of the absolute value of x plus c. This one's going to be the natural log of the absolute value of 2 minus 7x divided by negative 7. And then even further in that vein, if I asked you to say do the integral of 1 over 5 plus 3x to the 7th power, you might rewrite it first as the integral of 5 plus 3x to the negative 7th, but then it's just the same sort of stuff. We're going to use the anti-power rule, get 5 plus 3x to the negative 6 divided by negative 6. What other number do I need to be dividing by? 3. Because we know that if we took the derivative, the chain rule would make us multiply by 3. So that's what I was doing here. When I integrated 3 minus x to the negative second, I got 3 minus x to the negative 1 divided by negative 1. And then I also divided by the coefficient of x here because I know that the chain rule would make me multiply it by negative 1 when I took the derivative. That's what we're doing there. It comes up often enough that I think it is worth the effort to do it that way. All right. What else? Separation, sure. So, separable differential equations. So, good news for you all. On this exam, if the question says to solve the differential equation, you know it has to be separable. There's no other option. Now, that's different than a question that says maybe show that something's a solution, right? That doesn't matter what it is. You just have to find your thing, find its derivatives, plug them in as appropriate, and show that it works. But if the thing says solve, you know it's going to be separable. So let's start off with something like, sure, solve the following. Y prime equal to 3x squared times e to the negative y. So one thing, whenever you're solving a differential equation that you know is separable, you almost always want to write your derivative as in the Leibniz notation, right? The d whatever. So we should write this as dy dx equal to 3x squared e to the negative y. Whatever side your derivative is on, the thing that's on top has to stay on that side, and all those variables have to come to that side. So I want all my y's on the left, all my x's on the right in this particular case. So great, I'm going to multiply both sides by e to the y. So e to the y times dy, and multiply both sides by dx. I would also point out that once you get to the point, if you didn't start off at the point where you have dy dx isolated, but after you get to this point, the only things we're allowed to do are multiply and divide. Can't be adding or subtracting. Does not work.
Say I take this question and the y prime is equal to x squared minus u.
It's not separable.
No.
It's not separable. You cannot separate. So typically, if you had something like y prime equal to 3x squared minus e to the y, can't separate that. Because you have dy dx equal to that. And there's no way of pulling the y's to the left and the x's to the right without ending up with both on some of both on each side. Because if you try to like divide everything by e to the y, right, and if you add e to the y, you have dy dx plus e to the y equal to 3x squared. Now what are you going to do? Multiply by dx? Cool. dy plus e to the y times dx equals 3x squared dx. That's trash. Can't do that. But the good news again is you shouldn't be faced with this, right? There shouldn't be solving a differential equation problem where you're stuck with this kind of. Now we try to make it trickier, and we'll see that in the next example. But you should always be able to separate any differential equation you're trying to solve on this example. It's great. There's something else I felt like I want to say here. Guess not. So after this, we integrate both sides. Integral v to the y dy equals integral 3x squared dx. Integral v to the y is e to the y. Integral 3x squared is x cubed plus c. We always put the plus c on the independent variable side. So we're trying to solve for y, put the plus c on the not y side, or whatever the letters are. Now we solve for y, we take the natural log of both sides, so you get y equal to the natural log of x cubed plus c. And without an initial condition, we'd be done. If there was an initial condition, say they gave us something like y of 0 was equal to 2, then we'd plug in 0 for x and 2 for y and solve for c. So we plug in 2 for y, 0 for x, solve for c. It would probably have been better if I'd done it at this stage. Right? If I plug it in there, I get e squared equal to 0 plus c. Oh, c is going to equal e squared. Exactly like it's going to be here as well. So either way, I get e squared equal to my constant. So then my final solution is going to be y equal to the natural log of x cubed plus e squared. When you're solving differential equations at all, the constant over here is kind of tricky sometimes. If you're adding a constant to it, or subtracting a constant from it, or multiplying by a constant, or dividing it by a constant, we don't really change it. Because a constant plus a constant is still a constant minus a constant is still a constant times a constant is still a constant. But if you're doing something functional to both sides, like taking the natural log of both sides, or taking the square root of both sides, or taking the reciprocal of both sides, then that constant does get carried along in that function. So anything that's not the four basic operations, multiplication, division, addition, subtraction, by a constant, anything other than that, you kind of have to make sure the constant goes along for the ride. Let's look at another example. Is that one going to be terrible? Sorry, one sec. Let me just look at my examples here. That was terrible. Sorry, I'm trying to. So actually, that's a good question. So let's the tank problems. So a tank problem, depending on the situation, can be a first order linear or can be separable. Basically, and so let's look at an example here, and then we'll kind of talk about when you may or may not do this. So so here's my situation. We've got a tank. Initially holds 100 gallons of solution with 10 pounds of salt dissolved in it. We're going to add a solution with a concentration of 2 pounds of salt per gallon at a rate of 4 gallons per minute. We also drain the tank, drain the well-stirred mixture solution. And here's the important part, or the part that makes the difference, at the same rate of 4 gallons per minute. So, important side note here. If the rate you're putting stuff in and the rate you're taking stuff out is the same, you can always solve this you can always solve it as a separable differential equation, or you can do it as a first order linear. If those rates are different, you cannot solve it as a separable differential equation. Let me show you what I mean. So let's first write the equation. So we're going to let, so we'll say that S of T is the amount of salt in the tank at time T. In my opinion, it is very important that the thing you're thinking about how it's changing is the amount of stuff, not the concentration or percentage of stuff. It's more challenging to do if you try to do it in a different way. So S of T is the amount of salt at time T, and we're going to write a differential equation for how the amount of salt is changing. So the rate of change of salt is equal to how much salt you're putting in every minute minus how much salt you're taking out every minute. How much salt are we putting in every minute? Well, we're putting in a concentration that's 2 pounds per gallon at a rate of 4 gallons per minute. So we're putting in salt at 2 pounds per gallon times 4 gallons per minute. That's how much. So every minute we're putting in 8 pounds of salt. A lot of salt, depending on your tank size. How much salt are we taking out? Well, this is the part that's always a little bit challenging. Still concentration times rate. The concentration going out is the part where you actually have some sort of variable. The concentration going out is the amount of salt, which is S of T pounds of salt, per the volume of the tank, which is staying a constant 100 gallons, because we're taking out 4 gallons and putting in 4 gallons every minute. Rate of change of salts. That's what the ROC is for. This is the rate in, and this is going to be the rate out. So it's the concentration going out, which is the amount of salt divided by 100 gallons, multiplied by the rate it's going out, which is 4 gallons per minute. So our differential equation looks like ds dt is equal to 2 times 4, which is 8, minus S times 4 over 100, which I'm going to reduce down to S over 25. And this equation, this differential equation, is separable. It's kind of annoyingly separable, but if you only have one variable on the other side, it's always separable. You can just divide both sides by the entire right-hand side. It's kind of gross, and I'm going to show you a better way of doing it, but you could separate this as, because I don't know what S is equal to, right? S is the function, right? So I don't, right? So the thing is, if we're separate, right? If you're going to integrate both sides, one side has to have T's, one side has to have S's. So I can't just bring the dt over here and leave the S on that side. It's not the right variable matching. So the less nice way of separating this, which we're going to do better, the less nice way is say, cool, 1 over 8 minus S over 25 times ds is equal to 1 times dt. It's kind of gross, but it's totally doable. And based on what we said before, we could definitely integrate both sides of this, and the integral of 1 over 8 minus S over 25 would be the natural log of the absolute value of 8 minus S over 25 divided by negative 1/25. But there's a slightly better way of doing this. Get a common denominator over here. So a better way of writing this would be ds dt, 8 times 25 is 200. We can write this as 200 minus S all divided by 25. And then we could just bring the 200 minus S to the left and the dt to the right. We can rewrite this as 1 over 200 minus S times ds equal to 1 over 25 t. And be careful that your S's don't look like your 5s.
This is as complicated as you can do this.
Pretty much, yeah. Yeah. As far as setting up and solving. I will point out, when we talk about first order linear stuff on Thursday, even though you can solve this as a separable differential equation, I think it's easier to solve it as a first order linear. It's not always an option, but for these tank problems, specifically when the rate and the rate are the same, you can always do it either way. That's usually not a choice. And if you have the choice, it's usually computationally easier to do it as a first order linear. We're not going to do that today, not because I don't want to, but because, right, it's not going to be on your exam. Like, as much as I would love to talk about it, it's not what we should be doing today. But definitely on Thursday, I'm happy about that. Solving it separately, here's what we're going to do. We're going to integrate both sides. Integral of 1 over 200 minus s ds equals the integral of 1 over 25 dt. I'm going to do the thing I say I should always do. We're going to integrate both sides, and we're going to ignore the absolute value sign that would be on the natural log here. So we're going to get the natural log of 200 minus s, still divided by -1, which is the same as multiplying by -1, equal to 1 over 25 times t plus a constant. Now we're going to multiply both sides by -1. So the natural log of 200 minus s is equal to -1/25 t. -1 times a constant, still a constant. Now we're going to e both sides. So you have 200 minus s equals e to the -1 over 25 t plus c. And this next two steps are really important. We're going to rewrite the right-hand side as e to the -1 over 25 t times e to the c, and then say that e to the c is some new constant. I like to call it a, so does Dr. Didel. This is a times e to the -1 over 25 t. Now we can solve for s. So 200 minus s is equal to that. So I like to add s over and subtract that over. So 200 equals s plus a e to the stuff. And s is equal to 200 minus a e to the -1 over 25 t. Now we can finally solve for our constant. So we have to go back and plug in there. So this is our s of t. And we had an initial condition that the tank initially had 10 pounds of salt in it, meaning at time equal to 0, s is equal to 10. So if I plug in 10 for s and 0 for t, I get 200 minus a times e to the 0 is just 1. So great, a has to be 190. So our final solution here is going to be that s as a function of time is equal to 200 minus 190 e to the -1 over 25 t. Not too terrible, but it's not the best. Usually though, again, a lot of the times in this type of problem, it's more typical that you would get asked just to set the differential equation and not solve it. Not that you couldn't solve it, but you might not be asked to solve it. Right. Yes. Right. You're correct. I did not. Because this constant divided by -1 is still a constant. I just called them the same thing because that's what we always do. But if you call this negative c here and done all the work through, it still would have worked. You would have had e to the -c here, which would still be a constant a. So it all works out in the end. Correct, exactly, yeah. Because if I took the derivative of this, the derivative of negative natural log of 200 minus s is going to be -1 over your stuff times the derivative of the stuff, which is -1. Negatives cancel out. Yeah, exactly. Yeah. Sure.
concept, particle, reaction.
Mhm.
If you have a square, plus one, and if you're trying to get it top, would it be to see that plus B or?
So, yeah, it would.
Could you follow up question?
Sure, yeah. So, yes, let's do that first, actually, and then we can come back to that one as well.
There's a follow-up.
Sure. Okay. Oh, there's a partial fractions one?
Yeah.
Oh, yeah. Is it L? Or yeah. So yes, so this is 9L from the practice sheet. The integral of 3x squared minus 2x plus 3 over x minus 1 times x squared plus 1. Sure. Kind of an unexciting partial fractions problem, in my opinion, but that doesn't mean it's not something to do. So we just set up our whole fraction equal to a over x minus 1 plus not just b, but since it's an irreducible quadratic factor, right? X squared plus 1 can't be factored. It doesn't have any real zeros. It's a bx plus c over x squared plus 1. Okay, let's talk about what's going to happen before we do this. If you're unlucky enough that your b and your c are both not 0, then you have to split it up. Meaning, when you integrate this, you're actually going to integrate it as a over x minus 1 plus bx over x squared plus 1 plus c over x squared plus 1. Always. No ifs, ands, or buts. Like, you have to break up your x squared plus 1 into two pieces if they're both not 0. And then I'll point out so in fact, let's just finish the integral before we even do the partial fraction decomposition. Here's what we're going to get. You're going to need a times, what's the integral of 1 over x minus 1? The natural log of the absolute value of x minus 1. Plus b times the integral of x over x squared plus 1 is a u substitution, and it ends up being 1/2 the natural log of the absolute value of x squared plus 1. And then the integral of c over x squared plus 1 is c times the arctangent of x. And that's just how it's going to work out. So you can actually do the integration before you do the partial fraction decomposition. It's kind of weird, but you totally can. You might be wasting your time, though, if any of them are 0, right? So you don't want to do more work than you have to do. But I just want to point out that if we know what a, b, and c are, then we know what the integral is. And it is true that the integral, I just want to make sure everyone's super clear with this, that the integral of x over x squared plus 1 is just 1/2 the natural log of the absolute value of x squared plus 1. If you took the derivative of that, you'd get 1 over x squared plus 1 times 2x, and the 2's would cancel to get x over x squared plus 1.
You consider x squared plus 1 as u.
Right, you could do, yes, this is a u substitution problem. I'm just not doing the u substitution. I'm like, we know that the top is the derivative of the bottom. Let's skip the u sub. But yes, you totally could do u equals x squared plus 1, du equals 2x dx, so du divided by 2 equals x dx, and then this becomes exactly the integral of 1/2 du over u, which is 1/2 natural log of u, which is exactly what we got. But most people are cool with you skipping that because it seems relatively easy. And I'm like, yeah, that's easy. They should just think that's fine, no problem. So let's do the partial fraction decomposition. Multiply both sides by the common denominator. What's always going to happen is you're going to get the numerator of the left-hand side. And then each piece over here, you cancel the part that has the denominator and you multiply by the rest. So you're going to get a times x squared plus 1. And you're going to get bx plus c times x minus 1. That's kind of a tricky problem, in that you have less information than you often would. So in this problem, there's only one nice value of x to plug in, and it's x equal to 1. So we plug in x equal to 1, we get 3 minus 2 plus 3 equal to a times 2. And once one of them isn't 0, the rest of them should be 0, right? Bx plus c times 0 is 0. So here we get 2 times a is equal to 4. So a is going to equal 2. Now we don't have any other convenient values of x to plug in. You could pick other values of x. It's not my favorite way of doing it. So let me show you what I prefer, and then if you want to do it another way, we can. So what I think we should do after this is start equating coefficients. So the highest power of x on either side is x squared. On the left-hand side, the coefficient of x squared is 3. On the right-hand side, if you multiplied it out, you would have an a times x squared. You would also have a b times x, which is a b times x squared. Or in other words, a plus b equals 3. Which means, since we know that a is equal to 2, b has to equal 1. This is the most efficient way of doing it. And then if we still have things to find, we go down to the next highest power of x. The reason you pick the highest powers is there's usually less terms to work with. I don't love multiplying this out. Like, I clearly haven't. But if you wanted to, you could actually multiply it out and say you have ax squared plus a, and then you have bx squared minus bx plus cx minus c. So actually here I'm probably, no. So if we look at that, if we look at x, well, the coefficient of x on the left is -2, so I have a -2x on the left. On the right-hand side, I have a negative bx plus cx. So I have a negative bx. So -2 is equal to negative b plus c. Since b is equal to 1, c has to be -1. So -2 equals -1 plus c. So c is equal to -1. We found the 3 things. Now we're going to do the integral, but we already know what the integral is going to be, right? So then we would rewrite it as the integral of a, which was 2 over x minus 1, plus b, which was 1 times x over x squared plus 1, plus c, which was -1 over x squared plus 1. And I will again say, it is absolutely 100% vital that you break that up into 2 separate fractions. Bx divided by x squared plus 1 plus c divided by x squared plus 1. There is no other way of dealing with it. Or there's none other that way. I guess there could be. No. It's not going to happen. But here's what if you really want to know, it's unfortunate. It's a really stupid problem. It's actually, so just to point out, if you had something terrible like this, we're not going to finish this problem. It is a partial fractions problem, but you can factor that. So the thing is, there's no irreducible cubic factors. This factors as x plus 1 times x squared plus x plus 1. Minus, sorry, there's a minus there. That's how that factors. And then you would do this as a over x plus 1. And unfortunately, this is an irreducible quadratic factor as well. It's just more annoying. Right, terrible. You don't want to, this problem, no one wants to do this problem. Least of all me. But that's how that factors. It's kind of gross. It's actually really gross. Because then integrating this is much, much worse than a nicer one like x squared plus 1. Yeah, don't do that. Not say it's impossible, just it's not a good test question. And then you could finish this off, right? It's going to be 2 natural log of the absolute value of x minus 1 plus 1/2 natural log of absolute value of x squared plus 1 minus the arc tangent of x plus c. Don't forget those plus c's, right? You need those plus c's. If it's an indefinite integral, gotta have that plus c on there. I know there's some stuff about Desperate Housewives there. There was another question about another sugar, yeah. Is it one of the ones on his okay. Oh sure. Oh, I just wasn't seeing it. It's number 7 here. Well, they're not easy to create, so I'm happy to look at number 7 here. So let's read what the question. So for a problem like this, as I've heard some of my friends say, you want to go slow so you can go fast. Meaning, take the moment it takes to actually read all the words before you just start attacking it. So if I look at this problem here, number 7, I'm going to read it before I write anything down. Let S be the amount of pounds of sugar in a tank at time t. a solution containing 2 pounds of sugar per gallon begins flowing into the tank at a rate of 5 gallons per minute, and the well-stirred mixture flows out of the tank at the rate of 3 gallons per minute. Noting that the rate in and the rate out are different. Initially, the tank holds 100 gallons with 20 pounds of sugar. Set up, but do not solve a differential equation with the initial conditions for the rate DSDT. Interesting. I don't know about that. So great. We're just setting up here. We're not actually trying to solve this, which we couldn't anyway, because we know it's when we can't solve because the rate in and the rate out are not the same. Okay, so let's set it up. I would like to draw a little picture. We know that we're putting stuff in the tank at it's 2 pounds per gallon at a rate of 5 gallons per minute. The concentration going out is going to be the amount of sugar divided by the amount of volume, sorry, you can't quite see that, apologies, times the rate going out, which is, I believe, 3 gallons per minute. And starting off in the tank, maybe should have done it first. Initially, the tank has 100 gallons with 20 pounds of sugar. Okay. The only really challenging part of these problems is this piece right here. At least that's my opinion after doing this for a number of years. The part that you still have to really think about is what your S divided by your volume is. And this one is even more challenging because your volume is going to be changing. Because every minute we are putting 5 gallons in and taking 3 gallons out. So every minute we are adding 2 gallons to the volume. So we know that the volume at any time t is going to be 100 plus 2t. If it was switched and we were putting in 3 gallons per minute and taking out 5 gallons per minute, it'd be 100 minus 2t. So make sure that, right, if your volume's increasing, it's your volume plus your multiple of t. If your volume's decreasing, it's your number minus that. Okay, so then our differential equation, ds dt, the rate of change of sugar, is just equal to how much sugar is going in minus how much sugar is going out. So the sugar going in is 10 pounds per minute. I would still write it out like maybe I would, depending on the amount of time you had. Like I like to write it as 2 pounds per gallon. I usually don't like to include units, but I do here just to kind of make sure that things are making sense in my head. 5 gallons per minute minus the volume going out is going to be S of t, which just stays as S of t, right? You don't get to put in something for that. We're trying to solve for that. V of t, though, is 100 plus 2t multiplied by 3 gallons per minute. Or if you didn't want the units in there, ds dt would equal 2 times 5, which is 10, minus 3 times s divided by 100 plus 2t. Make sure that your s's look like s's, not like 5s. And if they look too much like 5s, write s of t. So it's really obvious that it's not a 5. Because my s's unfortunately just look too much like 5s. Or at least my 5s look too much like my s's. That's it. That's the whole problem. Oh, actually, I should back up 1 second. Because the problem said, set up and do not solve a differential equation with initial conditions for the rate ds dt. I don't know where it says to include the initial conditions here. So you might write this and also s of 0 equals 20 to include the initial condition. That's what I would do. I don't know what, I don't know what else they mean by that. So, right, because when you're setting up a differential equation, you set up the differential equation, and then I guess if you're including the initial condition, you'd be like, well, bam, there's the initial condition, but there's nothing else to really do. You can't insert that information into the problem. There's nowhere for it to go. Until you've solved it, which we're not being asked to do. All right. What else?
Another question like on your document here where it asks if patients continually receiving the drug through an IV could if the drug eliminated along 5 weeks.
Sure. So yes, I will say that problem is specifically unique in the way it's phrased, because they're asking you to set it up in a way so that the amount of drug remains constant. I don't remember exactly how it's phrased. But it's phrased very similarly to the one that he has, I think, here, right? Number 12 from his handout. A patient is continually receiving a drug. If the drug is eliminated from the body over time, so the fraction that remains after T hours is e to the negative 0.4 T. At what constant rate should the drug be administered to maintain a steady level of the drug in the bloodstream? I will also point out the one for my practice exam was taken from the last time he gave this exam. So it seems like a pretty decent bet that if you ask this question, it's going to be asked in this way. So let's change the numbers here, but the changing the numbers really doesn't change the process. So let's do it. So we have a survival. This is a survival renewal problem. Do you have to know the survival and renewal equation? Okay, great. So to take the words, a patient is continually receiving a drug. If you watch me go over the solutions, you might have seen me stumble here because I was like, oh, what do we do again? I have to like kind of figure out, but it's not hard once you know what to do. Continually receiving a drug. Okay, if the drug is eliminated from the body, over time. Okay, here are the important words. So that the fraction that remains, right, after T hours is e to the negative. I'm going to change the number to e to the negative 0.6 T. Right. The fraction that remains, that's what's telling you that it's S of T. So our S of T is e to the negative 0.6 T. At what constant rate? So when you read those words, you should be like, great, that means my R of T should just be a constant. Let's call it R instead of writing R of T. At what constant rate should the drug be administered to maintain, and this last part's important too, maintain a steady level. That's the other kind of key phrase here. Steady level of the drug. So what that part there means is that the amount of drug in the system at any time t is equal to the initial amount of drug. So that your P of capital T is equal to your P naught. Those are kind of the key observations you have to make to be able to do this problem. So now we're going to take our general survival renewal equation, which looks like this, that P of T is equal to P naught times S of capital T, so that's the P of capital T there, plus the integral from 0 to T of S of capital T minus lowercase variable t times R of T. And replace it with all the things we have. So right, this is the equation you're given. So we're going to replace everything we can with the stuff that we know it's equal to. So we're going to replace capital P of T with P naught. We're going to replace capital S of T with e to the negative 0.6 capital T. And we're going to replace capital R of T with just capital R. And S of capital T minus T is going to be e to the negative 0.6 times capital T minus T. And then our job is to solve for R. And what's going to end up happening is some stuff is going to cancel pretty nicely. And there's a few different ways to make this work out. Sure. So here's what we've got. We've got P naught equal to P naught e to the negative 0.6 capital T plus the integral from 0 to T. I would just bring that capital R out in front because it is a constant. And then S of T minus T is going to be, let's write this as e to the negative 0.6 capital T, which is also a constant, and then e to the positive 0.6 lowercase t. Let's do a little bit of simplifying. So I'm going to bring this over to the other side. So I have P naught minus P naught e to the negative 0.6 t. plus I'm gonna bring out this constant term before I do the integration. Yeah. Thank you. Yes, equals, good call. Positive r times e to the negative 0.6 capital T times the integral from 0 to t of e to the 0.6 lowercase t. Which I probably could have done the integration in that step, but I didn't. On the left-hand side, I do think it's probably necessary actually to factor out that p naught. So that the things that are going to cancel end up canceling. So on the left-hand side, p naught times 1 minus e to the negative 0.6 capital T equal to r times e to the negative 0.6 capital T. And then the integral of this is going to be e to the 0.6 t divided by 0.6. This is definitely a time where you don't want to be taking the time to do that u substitution, right? There's already so much going on here, kind of, that you're like, no, I don't want to do that. Evaluate it from 0 to t. I'm going to pull out the 0.6 in front and write this as p naught times 1 minus e to the negative 0.6 t equal to r times divided by 0.6 times e to the negative 0.6 t times plugging in the capital T first, I get e to the 0.6 capital T minus plugging in the 0 second, I get e to the 0, which is 1. And at this point here, there's one thing you need to do to make your life much easier. Distribute this through. If you distribute that through, look what happens. You get p naught times 1 minus e to the negative 0.6 t equal to r over 0.6. And then e to the negative 0.6 t times e to the positive 0.6 t is 1. And e to the negative 0.6 t times negative 1 is negative e to the negative 0.6 t. And those are the same. And they cancel. Right? Divide both sides by that. Solving for r, you get that 0.6 multiplied by p naught is equal to r. Whenever you do this problem, if it is phrased this way, so basically, if your s of t is some e to the negative a times t, and everything else is the same, your final answer should look like r is equal to a times p naught. That's always what happens with this problem. So yeah, I would be willing to bet a large amount of money that this problem will show up on your exam with whatever number happens to be in front of t, but not all my money. Right, it's pretty likely, but I mean, it's not, right, no guarantees. You don't know what's going to be on the test until you actually see the test, unless your professor tells you. All right, what else seems worthwhile? Sure, which I'm never very good at. I don't. Again, I don't think it'll be on there. I never remember the cardiac output formula, to be perfectly honest. Right? It's like, isn't cardiac output? It's like your flow or your flux or whatever equals the amount of dye divided by whatever the integral is. But like, yeah. Integral what t? But of what? Like what's the thing what's the function that's in it? See, oh, the concentration, that's right, yeah. The cardiac output isn't that bad. I will also point out that the Pousset's law question that I put on the practice exam, that also directly, or the one about like finding the maximum velocity, that is a direct transcription from the previous exam he gave. And it's not that hard to maximize a function. That's something we did in 17, right? Take the derivative, set it equal to 0, solve for your variable. What else on here? Sure. What about if I gave you something like dn dt equal to, sure, 6n minus 5n squared minus n cubed. That look all right? I think so. Yeah.
That one, the velocity one, I know you could take the second derivative and find, like, and show that.
Right.
Do we actually need to show that? Because he told us in class that when the radius, which is the middle of the vein, 0, you have the highest velocity.
Sure.
so we don't have to show no equal.
Well, I mean, oh, like to show that it is a maximum?
Yeah.
I mean, right, I would just say, yeah, like, yes, it seems reasonable that it should be a maximum, not a minimum. You could also, yeah, I suppose the other way of doing that, let's look real quick here. Where'd it go? Right, so, right, yes, I kind of was in my head about that one, but like, if you're given this, your V of R is equal to, yes, this P over 4 eta L times R squared minus R squared. And we found the critical point to be 0, I think, right? Did we? Good question, James. What'd you find? Yeah, so if you take the derivative set equal to 0, so V prime of R is going to be this constant times -2R, set that equal to 0, you get R equal to 0. One way of doing this is what I said, taking the second derivative, showing it's a maximum. But you can also look back at your original function and be like, oh yeah, if I plug in any other value of R, it's going to be less, right? V of 0, which is P over 4 eta L times R squared, is maximal. I think kind of obviously, right? Any other value of R is going to make this quantity smaller. So I think that's reasonable to not have to go to the second derivative. I just kind of was already in that mindset when I was doing the solutions.
There's a lot of space, right? Like all.
That's also true. Right, and actually, that's a good point. That's a clue sometimes, right? If your question has not very much space, that means the teacher is expecting you to be able to do the work in that amount of space. And often that means that if you're thinking there's some long process to do this problem, there's another way that's shorter often. So that's actually something good to look out for. I always say, if we have this kind of thing, if we wanted to find and classify the equilibria both ways, we could totally do it. So to find the equilibria, what do? Set it equal to 0 and factor. I can factor out an n, let's say a negative n. I'm left with a positive n squared plus 5n minus 6. And then I can factor that further as n plus 6 times n minus 1. So let's think my equilibria are n hat equal to 0, -6, and +1. And then do the usual thing. If I'm doing it graphically, -6, 0, and 1. I'll point out that this is a cubic function. And the leading coefficient is negative, meaning it's got a downward shape from left to right. So we know that this cubic function should look like vaguely like this. And I don't have a choice. Nice polynomial. Or you can test a point, right? You could have tested something like n equal to 2, but again, if I plug in n equal to 2 here, negative, positive, positive. So the whole thing's negative. So over here at 2, right, I'm getting negative values. And then each of these factors has an odd power, so we know that it's going to cross the horizontal axis every time. So then we know that both -6 and +1 are stable. So these two guys are stable. And 0 is unstable. Sure.
How do you know if it's unstable or stable? Do you just look at the graph?
Yeah, so there's two ways. So graphically, you can tell it's stable if the graph goes from positive to negative. Because look what's happening, right? What are we actually graphing here? We're plotting dn dt, the rate of change of n, against n. So if dn dt is positive, that means n itself is increasing, moving further right. If dn dt is negative, n is going left. Dn dt is positive right, negative left. So the points where the arrows are pointing towards it are the stable ones, and the points where the arrows are pointing away from it are unstable. Here's a question I bet you would ask. I don't have enough. So for this problem here, if n of 0 is equal to 3, what is the limit as t goes to infinity of n of t? Which we have not solved before. This is where the phase plots are really super useful. So if we start at 3, we're going to get pushed towards 1. If instead n of 0 was, say, -3, then the limit as t approaches infinity of n of t would be what? Right. In this example I've come up with, they're all, your limits will always be a positive constant because you have stability kind of on the other side. But in a different example, you might have, like, you might be over here and be pointing to the right, and then the limit would be positive infinity because you get pushed way out that way. Okay.
What kind of perfect way to show this, or unless it's fine, just say.
I think this is all you need, right? Based on the fact that you could say so, like, for example, here, I could say because if n equals 3, dn dt is negative and 1 is an equilibrium or the nearest equilibrium.
What if your
But I don't think you need around all that.
is like in between, like, two sides? What if it's like in between, one side's going to the other, like one side's going towards the left, one side's going to the right?
So what do you, I'm not sure what you mean exactly. Like if I had something like where, like say this might, like if you're going,
It's closest to.
well, it depends.
Okay, smack in the middle.
Well, so, but you can't be pointing that. So the thing is, the way you're pointing is based on whether the graph is above or below the x-axis. So if you've got something like this, which way do you have to be pointing underneath it?
Right.
To the right, because the graph is positive. You don't have any choices. Now, I will, the one other thing I'll say here is if you have something like, sure, let's say I have another one over here. Like that would be unstable because your graph is pointing left and still left. So it has to be, both sides have to be pointing in towards your equilibrium for it to be in equilibrium.
Criterion. I can find the derivatives of the G of Y and then.
Yeah. So the other way of solving this, I was going to try to get to where we're kind of at, was if you take your, right, if you take your g of n equal to 6n minus 5n squared minus n cubed, take the derivative of that, which is 6 minus 10n minus 3n squared. And then if you plug in, say, for example, g prime of 0 would be 6, which is positive, so it's unstable at 0, right? Because if it's positive, it's unstable. And g prime of, say, for example, positive 1, one of the other 2 points is going to be 6 minus 10 minus 3, which is -7, which is negative, so it's stable. That's the other way of showing you. But I'll point out that totally tracks to, oh yeah, look, that one's stable and clearly the derivative there is negative. Oh, look, that one's unstable and clearly the derivative there is positive. Stable, derivative is negative. Go ahead. All right. Yeah.
For the graph that you do on the bottom.
Which I just made up.
Yeah. But if you were to find the limit of like the function or given there, would the function are stable?
Well, again, it depends on where you start. Right? So here, being told that n of 0 is equal to 3, I'm starting here and then just going in the direction that the arrow is telling me to go until I get to an equilibrium. Or if you had something that was like, if I had, say, something like that, for example, if I was told that, n of 0 was equal to 0, I'd be starting here and I'd be going to the left. Sorry, yeah, my right, your left. And so in this case, the limit as t goes to infinity of n of t would be negative infinity. Because n is just getting more and more negative.
If it's the initial condition is on the very right, would it go to the one stable equilibrium? Not that one.
Yeah, it would go there.
It would just pass over there.
Yep. All right. Make sure you take that practice test I wrote. And good luck on your exam tomorrow.